Hello guys, this is Avinash and in this video we'll deal with the extraction of aluminium. In the previous video I have started about the different extractions. Okay, so we have finished extraction of magnesium and in this video we'll deal with the extraction of aluminium. Okay, so basically we'll see what are the different ores of this. Okay, the different ores are gibbsite, that is nothing but Al2O3.3H2O. It means trihydrate of alumina is gibbsite and the other one is diaspore. This is monohydrate. There is only one H2O molecule is present. Okay, so these are the two different ores, and the most economical ore, that means the ore from which we generally extract, is bauxite. Bauxite is nothing but the mixture of these both, mixture of gibbsite as well as diaspore. Okay, the mixture of gibbsite plus diaspore gives us the bauxite. So usually bauxite contains about 60 to 65% of Al2O3. Okay, so these are the different ores. So now we'll see what are the different applications. So aluminium, we know it is one of the most, not one of the, but the most abundant metal that is present in the Earth's crust is aluminium. Most abundant metal in the Earth's crust, that is aluminium. So it has lots and lots of good properties. Okay, so we know it is one of the light metal. That means it has a less density. Okay, that's why we call it a light metal, and it also has an excellent corrosion resistance. That's why we can see aluminium in the surroundings. That means even in atmospheric conditions aluminium can be used. Okay, so that's why we can see more and more applications of aluminium in the room temperature, and also it is one of the best or very good thermal and electrical conductor. Okay, it is one of the best electrical and thermal conductor. Okay, so we know usually copper is used, but in the absence of copper, we know copper is a bit costly. So in the absence of copper, aluminium is used. And if you require the sequence, the most conductive metal is silver, then copper, then gold, and then comes aluminium. Remember this. Okay, so silver, copper, gold, and aluminium. This is the sequence of the conductivities. Okay, so this is one of the important property of aluminium. Okay, so usually this aluminium can be casted, rolled, and also mechanically deformed into various shapes. So that's why it is usually used for daily purposes. Okay, now in magnesium we saw two types of reactions or two type of extractions. One is carbothermic and other is metallothermic. So here usually carbothermic is not utilized for aluminium, and there are some reasons also why it is not. So now we'll discuss about why carbothermic reduction of aluminium oxide has not been commercially adopted. Okay, so the main reason is it requires a very high temperature. Temperature of about greater than 2000 degrees Celsius. Okay, because we are dealing with alumina, that is Al2O3, the melting point of alumina is itself 2040 degrees. Okay, so to produce liquid aluminium we require temperature greater than these. It is highly impossible. Okay, and one more thing is at this temperature, undesirable components are formed. What are those components? Undesirable carbides, okay, of aluminum are formed. That means instead of extracting pure metal, we'll be getting aluminum carbide. So that is why it is also not feasible. And finally, at this high temperatures, we don't have any stable refractories. Even though we have some refractories, those are highly expensive. Okay, so these are highly expensive and usually not readily available. Okay, that's why, because of these three reasons only, therefore, the carbothermic reduction of Al2O3 is not feasible. Why? Because it requires very high temperature and it forms undesirable carbides of aluminum at this high temperature, and also refractories is one more problem. So that is why the carbothermic reduction is out of our topic. That's why carbothermic reduction of Al2O3 is not at all adopted. Okay, and one more thing, so many of them can get it out about electrolysis. We can do electrolysis and separate these, but what happens from the EMF series, usually Al plus 3, right? Okay, Al plus 3 is the cation, you can say, and this is usually evolved or deposited at the cathode. Yes, the cations are deposited at the cathode, but in the electrolyte, obviously there will be some H plus ions present. Why? Because in the ore itself we have some water molecules. So this has very, or hydrogen has zero potential, whereas aluminum requires some amount of voltage. So in this electrolysis process, what happens if we do some electrolysis of bauxite, then hydrogen gas will be evolved at the cathode instead of the aluminum metal. That is why electrolysis is not at all feasible to directly do from the uh, what we call the ore of aluminum, that is bauxite. So that is why there is a universally adopted process for the extraction of aluminum, and now I'll be explaining about what is the process. Okay, first we'll see the flow chart, that is how from the ore we can extract the final metal, then I'll explain each of them. So firstly, what we have, the ore itself, that is we have bauxite. So usually bauxite is taken into process of a hydrometallurgical route known as Bayer's process. Okay, it is a hydrometallurgy. I'll explain what is this Bayer's process. Now bauxite is taken into Bayer's process in the hydrometallurgical route, or you can call leaching. Okay, we know we have pyro, hydro and electro. Depending on the source of energy, there are three different categories. Pyro, the temperature is the source. Hydro, leaching is done. That means the chemical reactions between the solution will be providing the source of energy. Similarly, electro, the electricity. Okay, so here, firstly, bauxite is leached to obtain pure Al2O3. That means whatever, if we do electrolysis, we know hydrogen is opposing for the deposition of aluminum, so we are getting rid of the hydrogen molecules or the H2O molecules. So that is why the bauxite is converted into pure Al2O3 through a hydrometallurgical route. And after doing this, after getting a pure Al2O3, then it is again, or it is taken in the same electrolysis or electrometallurgical route in order to obtain pure aluminum. Actually not pure, we cannot say pure aluminum. Okay, we will be getting a metallic form of metallic aluminum, which is again undergoing 3-layer refining process. Then you will get pure aluminum. And I forgot the name of this. The electrometallurgical process that is used is known as Hall-Héroult process. Okay, this is about the flow chart, or how the ore, that is the bauxite, is converted into pure aluminum. Firstly, bauxite is taken into leaching or a hydrometallurgical process known as Bayer's process to convert it into pure Al2O3, and this pure Al2O3 is again undergone an electrometallurgical process known as Hall-Héroult process to obtain the metallic aluminium, and this metallic aluminium is usually refined using this three-layer refining process, and this three-layer refining process is known as Hoops process. Hoops process. So we have three different processes. We'll discuss all these three now. Okay, after the Hoops process, we'll be getting pure aluminium. So now we'll start with the Bayer's process. Okay, so in this process, what happens? A high purity alumina that is required for electrolysis, that means for the raw material of the electrometallurgical process, we have to do this Bayer's process in order to produce that high purity alumina. So Bayer's process. Okay, so as I already said, pure Al2O3 is produced from the bauxite. Bauxite is converted into pure Al2O3. Okay, this is known as the Bayer's process. Now we'll see what is this Bayer's process. So usually in this process, bauxite is initially leached. Bauxite is initially leached with the help of NaOH. Leaching is nothing but the chemical reaction between these two. That means bauxite is allowed to react with NaOH at a condition of high pressure and also a high temperature. The pressure is about 25 atmosphere and the temperature is about 220 degrees Celsius. So that means the bauxite is leached with NaOH at 25 atmosphere pressure and 220 degrees of temperature to form sodium aluminate. So after this leaching, what happens? Sodium aluminates are formed. Sodium aluminates are formed. Okay, that means we know bauxite is nothing but the mixture, so there will be two reactions. This is nothing but the sodium aluminate plus some amount of water is liberated. Similarly, the other one is the monohydrate. It also reacts with the NaOH and it also forms the same 2NaLO2 plus 2H2O. Okay, and this leaching is usually done for 2.5 hours. Okay, so what happens? The bauxite on leaching with NaOH forms sodium aluminate, NaAlO2. Okay, these form sodium aluminates. So what happens? Whatever the leach liquor that is obtained, it is cooled to a very low temperature. That means whatever the solution we got here, okay, whatever solution we got here, it is allowed to precipitate. It is depressurized. Okay, so it is what we call depressurized in order to form crystals of pure Al2O3. Okay, so what happens is this sodium aluminate, this is again precipitated, and this is from this usually AlOH3 is formed. Okay, if you see the mechanism of this Bayer's process, the bauxite after leaching, there will be some amount of settling, filtration, thickening and all the processes, and finally after precipitation you will be getting AlOH thrice, that means aluminum hydroxide, and this undergoes calcination. Whatever Al2O3, it undergoes calcination, and what happens? Pure anhydrous Al2O3 is obtained. Then pure anhydrous is nothing but absence of water molecules. Okay, so pure Al2O3 is obtained from the bauxite by this process. This is known as the Bayer's process. Okay, so briefly if I explain it again, bauxite, from the bauxite, extraction of pure Al2O3 is known as Bayer's process. Bauxite is leached with NaOH under a condition of high pressure of 25 atmosphere and a high temperature of 220 degrees Celsius, and these reactions undergo, and finally we get sodium aluminates. Okay, so this liquor, this leach liquor is again allowed to precipitate, and on precipitation you will be getting AlOH thrice, means aluminum hydroxide crystals are obtained, and these are calcined. That means these are taken into calcination process in order to obtain pure anhydrous Al2O3. This is Bayer's process. Okay, now we got a raw material. Okay, whatever raw material we got, this will be utilizing in the Hall-Héroult process. This pure Al2O3, the which we have produced from the Bayer's process, it is taken into the raw material into the Hall-Héroult process. Now we'll discuss about the Hall-Héroult process. Okay, as I already said, Hall-Héroult process is a type of electrometallurgical process. Yeah, so this Hall-Héroult process is an electrometallurgical process. So I'll quickly draw the cell. So here it is nothing but electrolysis only that will be taking place. So I'll briefly explain about the cell. Okay, so if you consider this as a electrolytic cell, okay, because I said this is an electrolysis process, here these are the electrodes or anodes. Okay, here there will be a lining. Okay, here generally there will be a cathode lining. Cathode lining will be there, and this is again the ore insulation. Okay, so here we'll take the electrolyte and we'll pass on the electricity in order to obtain aluminium. Okay, now what is this electrolyte? This electrolyte consists of cryolite plus Al2O3. Okay, so the electrolyte that is used in this electrometallurgical process is known as, the electrolyte is a mixture of cryolite and Al2O3. Okay, so from this you'll be getting pure, or metallic aluminium, which is denser, and it will be settling at the bottom because this is the cathode, so it will usually settle down at the bottom. So now we'll briefly discuss about the cell operation. Okay, so during this operation, the cell bath is filled with this cryolite. Okay, first we must fill the volume of the cell with cryolite, and then the anode is lowered into it and current is passed. Why we first keep this cryolite? Because cryolite is usually, it must melt down. Okay, it melts at a temperature of about 990 degrees Celsius. Okay, this is the temperature of the cell. That means the Hall-Héroult process is done at a temperature of 990 degrees because this cryolite must be melting at that. So once the bath is attaining the molten state, then after the molten cryolite is produced, then we add the Al2O3 into this. Okay, that means we have to start the cell, we have to lower the anode, okay, and we have to pass the electricity. We must produce at a temperature of about 990 degrees Celsius, and once the whole cryolite melts, then only we have to add the alumina, that is nothing but the Al2O3. Now what happens? This alumina decomposes, reacts with the melt, and it decomposes because of the electricity to yield aluminium and oxygen. Okay, so obviously O minus 2 will go at the anode, and this aluminium which is formed will be deposited at the bottom on the cathode lining. Okay, so the necessary heat, whatever necessary heat, it is usually supplied by the resistance offered between the electrolyte and these anodes. Okay, so the current is produced. Because of the current, there will be some necessary heat. And now the most important part that is to be remembered is 5 to 10% L2O3 must only be utilized. Okay, it should not be less than 5. If it is less than 2 or 5, what happens? Then there will be no normal contact between the electrode and the electrolyte, and there will be a gas film produced between them. And this production of gas film is known as anode effect. Okay, and this usually they say if the Al2O3 content is less than 2%, then this anode effect is observed. What is this anode effect? Anode effect is nothing but formation of a gaseous film between the electrode and the electrolyte, between the anode and the electrolyte. Okay, so it results in no normal contact between these both. Okay, and usually along with cryolite, why we add cryolite is because to reduce the temperature. As I already said, the temperature is 990 degrees. But if you consider the melting point of Al2O3, as I already said at the beginning of the video, it is about 2000 degrees Celsius. Okay, it is more than 2040 degrees Celsius. So that is why cryolite is used. And also along with cryolite, there is other addition like calcium fluoride. Okay, why it is added? Because it increases the electrolytic conduction. Okay, cryolite is added for decreasing the melting point. Similarly, CaF2 is added to increase the electrolytic conduction, okay, of the melt. So these are the two important additions that are done along with Al2O3. Okay, so this is Hall-Héroult process, and from this what happens? We'll be getting metallic aluminium. The bottom one, okay, here there will be a metallic aluminium formed of purity 99.5 percentage. 99.5 percentage purity is obtained, but this 99.5 percentage purity is not sufficient for the application of electricity. That is why it should further be refined to 99.99%. That is why after the Hall-Héroult process, we do electrolytic refining of this aluminum, that is known as Hoops process or three-layer process. So now we'll discuss Hoops process. Okay, so it is usually electrolytic refining. Okay, and it has name Hoops process. Hoops process, or it is also known as three-layer refining process. Okay, three-layer refining process. So here also what happens, usually this 99.5 percentage pure aluminum is taken here, and here also there will be a cell actually. Okay, so usually what happens here, we'll be having an anode, that is nothing but the graphite electrodes. Okay, and here we have a carbon bottom. Carbon bottom will be there, and if there is any scrap, we can also add that here. Okay, and here what happens is usually three different layers will be formed on reaction on supplying the electricity. Okay, so usually if we see here, pure aluminum will be at the top. Okay, the electrolyte, whatever electrolyte we use, that will be there here, and copper aluminum alloy will be at the bottom. Okay, this is pure Al, this is electrolyte, the middle layer is the electrolyte, is the electrode. What is the electrolyte here? Electrolyte is again the mixture of this cryolite 30%. These are added to this. Okay, fluorides like BaF2, CaF2. Okay, and also LF3. These are also added. Okay, the electrolyte that is used for electrolytic refining is the mixture of the aluminum along with cryolite and other fluorides, and also some amount of scrap can also be used. Commercial aluminum scrap can also be added. Okay, so what happens, the pure aluminum has a density of about 2.3, that is why it is floating, and the density of this what we call the electrolyte, the density is about 4. Okay, whereas the density of this copper aluminum alloy is about 4.5. Okay, that is why what happens, it is usually at the bottom, and this copper aluminum alloy, aluminum copper alloy is acting as anode. Okay, it acts as an anode also. So from this, pure aluminum is taken from the top. Okay, so this is okay, the density of electrolyte is about 2.8. It's about 3. Okay, not 4, it's about 3. Okay, and the operation temperature is about 950 degrees Celsius. The temperature at which this refining is done is 950 degrees Celsius. So what we are doing here, the impure aluminum is alloyed with the copper, okay, and it is forming a bottom layer which reacts with this electrolyte. Okay, to give, it reacts, the continuous reaction between the electrolyte layer and this aluminum copper alloy is taking place, and what happens, pure aluminum is getting separated, and this pure aluminum is 99.99%. Okay, so this is the electrolytic refining of aluminum. Okay, so finally we have completed the flowchart. The flowchart is nothing but from base process we convert bauxite to pure Al2O3, and in Hall-Héroult process we convert pure Al2O3 to metallic aluminum of about 99.5% purity, and from that 99.5% aluminum we convert into 99.99 using Hoops process or 3-layer refining process. So this is the most economical and universally accepted and adopted process for the extraction of aluminum. So with this we have completed the extraction of aluminum. So if you like this video, please hit the like button and also share this video with all the GATE aspirants. Let them know about everything metallurgy, and I wish all the very best for your GATE examination. Do very well in the last 1 month. So thank you guys, thanks for watching.